Let's take a look at two different application problems that will use the derivatives of exponentials and log functions. So the first one is, an investment of $5,000 earns interest at an annual rate of 6% compounded continuously. So this is important, right, when it tells you that it's compounding continuously, because you know then that you have to use the investment formula, which is A is equal to PERT. Okay, find the instantaneous rate of change. Okay, so remember that's going to involve the derivative of the amount in the account after 3 years. So let's write what we have. So the 5,000 is the original amount. That stands for P. The annual rate is 6%. That stands for R. But in the formula, you have to put it in as 0.06. Now, these things are never going to change, right? This is set. So let me put this in. This is A is equal to 5,000 e to the 0.06t. So this is actually a function based on time because the time is changing, but your 5,000 and your 6% are never going to change. They are set. So you could actually write it as A of t is equal to 5,000 e to the 0.06t. T is the variable that's changing. Now, I want to find the rate of change, hint derivative, at 3 years. So first I need to take the derivative. So I have A prime of t is equal to, now remember on the side that if you have e to the cx and you're taking the derivative of this, this is c e to the cx. So in our case, c is 0.06, so it's going to give me 5,000 times 0.06 e to the 0.06t. And so that will give me 300 e to the 0.06t. But again, I'm looking at when t is equal to 3, so I need to plug in 3. So I have a prime of 3 is equal to 300 e to the 0.06 times 3. And that is going to give us approximately $359.17. So your account is increasing by $359.17, about $360 every at 3 years. Okay, so it's good. It's a good change there. Let's look at part B. Find the instantaneous rate of change of the amount in the account at the time the balance is 8,000. Now there are going to be two ways to do this problem. I'm going to show both so you can choose which way kind of makes more sense to you. Now in this case, they don't give you the time, they give you the future value. They give you what A is. It's $8,000. So one of the ways that you could do is first you could take your A of t, which was 5,000 e to the 0.06t, not the derivative, right, the regular function, and figure out the time when the account is 8,000. So you would set A equal to 8,000, and you would solve for t. So divide by 5,000, that's going to give you 1.6 ln both sides. So the ln of 1.6. On the right, we've done this a lot. You're going to be left with 0.06t because the ln and e are inverses. Divide by 0.06. And that's going to give us that t is approximately, and I'm going to write the full decimal, 7.833. Because I'm going to be using this, so I don't want to round, all right? So what I'm going to do is, now that I know the time, I can do what I did above. So I can find the instantaneous rate of change, right, which was right here, and I know what t is. So the only thing I had to do extra was I had to find what t, because I only knew that the future value was 8,000. So I have a prime of my 7.833 is equal to 300 e to the 0.06 times 7.833. And that's going to give you that approximately at that time, the instantaneous rate of change, your account is growing by approximately $480. Okay, now the other way, which is a little bit trickier to see, but I'll still show it to you, is to realize that a prime of t was 5,000 times 0.06 e to the 0.06t. And a of t was 5,000 e to the 0.06t. But this, which I'm going to underline in red, is right here. The only thing that's extra is that it's being multiplied by 0.06. So you can rewrite a prime of t as 0.06 times a of t. But you know that a of t is 8,000, which means that a prime of t at that time was 0.06 times 8,000, which is $480. This is much trickier to see. I think most of you will probably have gone for the other way, but I still wanted to show both. Okay, now a different type of question. A model for a newspaper circulation is given by the following function, where C of t is the circulation in thousands in years, and t equals 0 corresponds to 1980. Okay, that's important. Use this model to estimate the circulation and the rate of change in circulation in 2026. Okay, so the key here is that if t is equal to 0 corresponds to 1980, what is t when it's 2026? Well, you look at how many years have passed. So from 1980 to 2000 is 20 years. 2000 to 2026 is 26 years. So in total, that was 46 years. So we want to estimate the circulation. So we would do C of 46. That's going to give us 83 minus 9 ln of 46. You would use your handy dandy calculator and you would get approximately 48,000. Well, actually, I'm sorry, in your calculator, you're going to get, if you enter it, right? Because the key here, if you do 83 minus 9 ln of 46, it's going to give you 48.542. But it's in thousands, so you need to multiply this times 1,000, right? That's the key that you got to be careful when it comes to that. And you get then it's approximately 48,542. Don't forget to look at your unit of measure. Then you want to look at the rate of change in circulation. So that's derivative. So I'm going to have C prime of t is equal to 0 minus 9 times 1 over t. Because the derivative of ln of x is 1 over x. So it gives me negative 9 over t. So I have C prime of 46 is going to give me negative 9 over 46. So again, that's going to give you 8 decimal here. And when you do that, you're going to get negative 0.196, but then you multiply by 1,000 because it's measured in the thousand, and that's going to give you about negative 196. So to interpret our results, in 2026, the circulation is 48,542 and is decreasing because the rate is negative at a rate of 196 newspapers. Okay, so they're not doing too good, maybe the internet, right? So they're having a decreasing rate in their circulation here. So here are two different application problems.